Simple diffusion, it is a type of passive transport in which the substance they move from higher concentration to lower concentration, and in simple diffusion no energy is used for the movement of the substance. Simple diffusion can occur through channels, pores, or even through lipid bilayer. Even through lipid bilayer. So simple diffusion, the action words are channels, pores, and lipid bilayer. So if you come across these words, definitely they are a type of simple diffusion. Now, which type of substance move in simple diffusion? Simple diffusion is generally for the small ions or molecules. Simple diffusion is generally for the small ions or molecules. Ions or molecules which can cross the cell membrane or which can go through the channels or pores. Let us go with the first, channels. Channels are one of the integral part of the cell membrane through which the ions or molecules move. Just consider, let this be a cell membrane, and we have the cell membrane with an ECF and with an ICF, that is extracellular fluid and an intracellular fluid. Now, the substances which are water soluble, the substances which are water soluble or charged particles which cannot cross lipid bilayer, those substances they move across the membrane by channels, by using channels. Say for example sodium. Sodium is an ion. Sodium cannot move. Sodium is an ion and it cannot move through lipid bilayer directly. So for sodium we have channels. They are called as sodium channels. So whenever a sodium channel is available, the sodium ions will move from ECF to ICF. That is from outside to inside the cell membrane. That is from higher concentration to lower concentration. This movement of sodium is occurring through the channels. The channels, they are very important in a cell membrane because they give specificity to the cell membrane. The cell membranes have various types of channels. The channels can be specific for sodium ion. The channels can be specific for potassium ion, for calcium, or for chlorine, or for other ions. So these channels, they are very specific in terms of ions, and also they are specific in terms of their gating behavior. That is, when a channel will open or when a channel will close. So let us have some more detailed information about these channels. Channels are of different types. We have channels which are always open. Channels which are always open, they are called as leaky channels. So we have a sodium and potassium leaky channels through which sodium they keep on leaking from outside to inside, or potassium they keep on leaking from inside to outside. So leaky channels are the channels which are always open, inside the cell membrane. So for channels, the substance they just keep on leaking either from outside to inside or from inside to outside. Whereas there are certain channels which are gated. So we have a channels which have gates on them. Gates are like leads or like cap. So if a gate is closed, the channel is closed. The substance cannot move. If a gate is open, the channel is open, substance can move. So we have gated channels. Let us have a simple diagram for this. Suppose we have a channel. Say we have a sodium channel. And this sodium channel has got a gate. On it. Now once this gate is closed, the sodium ions cannot move through this channel. When this gate is closed, the sodium ions cannot move through these channels. But if the gate is open, then the sodium ions can move across this channel or through these channels. So the gate can be open or can be closed, allowing the substance to move either from outside to inside or from inside to outside. So channels have varieties in them. We have leaky channels and we have gated channels. These channels, whenever you get the word channels, they are simple diffusion, where the substances are moving from higher concentration to lower. So gated channels, when we are talking about gated channels are of various types. We have a gated channel, say number one, a gated channel which open the gates, which open or close on receiving an stimulus. We say a mechanical stimulus. Say touch. When we touch on the skin surface, touch is a mechanical stimulus. So the mechanical stimulus opens the gate and the channel is open and the substances are moving. That is sodium ion or potassium ion or whatever ion we can say. But the important thing is the gate is specifically opening because of the mechanical changes in the membrane or mechanical stimulus. Let us have one more example. The endocochlear cells. In the endocochlear cells, we have cilia. Those cilia, they move. They have a wave motion because of the sound waves. And because the cilia, they move, their mechanical movement causes opening of those channels on those cilia, and the endocochlear cells, they either get excited or they get inhibited, and the sound is being heard or the sound is being processed in our ear. So again, a mechanical movement. Let us write down the first one, mechanically gated channels. So we have channels which have gates, and the gates, they open and close on depending upon various stimuluses. So we have first a mechanically gated channels. We have a mechanically gated channels. A mechanically gated channel is a channel on which the gates are open on mechanical stimulus. Mechanical stimulus. Example, a touch receptor. A touch receptor will have a mechanically gated channels. And to be more precise, mechanically gated sodium channels. Or you can say endocochlear cells, the cilia of the endocochlear cells. So we have endocochlear cells, cilia, or we have touch receptors, we have joint receptors through which the substance are moving or the sodium ion is moving. So cilia of the endocochlear cell is another example for the mechanically gated channels. Remember, channels have a gate, and the gate, they open or close on a specific stimulus. So first one is a mechanically gated channel. Second type, we also have another type, and that one is the chemically gated channels or ligand gated channels. So we have a chemically gated channels or a ligand gated channels. Now what does a chemically gated channel is? A chemically gated channel is a channel on which the gates are usually closed, but the gates will only open if a particular chemical, say a hormone or a neurotransmitter, attaches to the channel. Say for example acetylcholine. Acetylcholine is a neurotransmitter. So when acetylcholine binds onto the channel, say this is a channel and this is a receptor, and the acetylcholine binds onto the receptor, the gates are open. Otherwise the gates would be closed. So in chemically gated channels, binding of the ligand, remember, binding of the ligand or binding of a chemical opens the gates. And when the gate is open, again the substance move from higher concentration to lower concentration. So we have a ligand gated channels or a chemically gated channels. Let us go with the third one. Let us go with the third one. Yeah, let us write down the example here first. So we have acetylcholine gated channels for sodium and potassium ion. Acetylcholine gated channels means the acetylcholine becomes a ligand, and acetylcholine receptor ligand gated channels which are present at neuromuscular junction on the muscle membrane. On the muscle membrane, we have these very specific channels which are ligand gated channels, and when the neuron releases the neurotransmitter, this transmitter is ACH. ACH binds onto the muscle membrane, and this opens the sodium channels, and the sodium channels enters the muscle membrane. We're going to discuss this process in very detail in the further sessions of nerve muscle physiology. As of now, we are studying the fundamentals of channels. Later on, how in every system the channels are working, we'll be discussing that in very much more detail. Third one, let us go with the third one. So, mechanically and chemically. Can you guess the third one, the third type of channel? We have mechanical channels, we have chemically or ligand gated channels, and we have the very interesting one, the fourth type is known as, the third type, sorry, is known as a voltage gated channel. A voltage gated channel. A voltage gated channel means a channel which will have a gate, a channel which will have a gate, but the gate will open only because of change in a voltage across the cell membrane. Means if we have a cell membrane and a channel, then the cell membrane, it distinguishes the voltage inside and outside the cell membrane. So we have some voltage inside and some voltage outside the cell membrane. So difference in this voltage in millivolts would open the channel, and the ions will move either from outside to inside or from inside to outside depending upon their concentration gradient. Okay, so this is a very huge variety. Now you can imagine the variety we have here. Okay, say we have mechanically gated sodium channel, mechanically gated potassium channel, mechanically gated calcium channels. We will also have a chemically gated sodium channel, chemically gated potassium channel, even chemically gated calcium channels. We will also have a voltage gated sodium channels, voltage gated potassium channels, and voltage gated calcium channels. So there is a very huge variety of the channels which are available on the cell membrane, and they are available on depending upon the function of the cell membrane. Let us go back to the voltage gated channel. So voltage gate channel are the channels in which the gate will open only if there is a change in the electrical voltage across the cell membrane, and this voltage change will open the gate of the channel, and the substance will move, or you can say sodium ion, for example, will move from outside to inside, or potassium ion will move from inside to outside. The very commonest example of voltage gate channel is the action potential. It is the action potential. Action potential is the change in the membrane voltage which causes excitation of the cell. We have heard action potential, and we'll be discussing in much more detail in the further chapters. So action potential can be one of the very excellent example of the voltage gated channel, and action potential specifically occurs because of the voltage gated channels. So we have completed so far three types of channels: a mechanically gated, a chemically gated, and a voltage gated. We are left with one more type of channel. Can you guess which type it would be? A gated channel? Yes, I'd like to hear from you. The fourth one is a time gated channel. A channel which is quite specific for time bound opening and closing. Time bound opening and closing. A time gated channel. Where do you find such type of channels? They are commonly found on the pacemaker cells, which are very specifically getting activated at a specific time. Say SA node. SA node is a pacemaker of the heart, and it has an excitatory activity of say 100 or 120 excitations per minute, which causes heart to beat at 70 or 80 or 90 or 100 times per minute. So pacemaker cells have a quite property of time gating behavior. Time gating behavior. So time gated channels are most commonly found on pacemaker cells. In fact, I would add one more point here. The mechanically gated channels or ligand gated channels or voltage gated channels, even they do show some sort of time behavior. How? If we say a voltage gated sodium channel, a voltage gated sodium channel and a voltage gated potassium channel, both of them have voltage property, but also a voltage gated sodium channels is quite faster in response. It opens and closes very fast. When the voltage change occurs, the sodium channels, they are first to open and first to close, so very fast in functioning, so their time is quite short. Whereas potassium channels, they are quite slow in opening and quite slow in the closing, so their time is quite prolonged. So even though they have very specific types, the gates, they also share some of the common properties among each other. So we have mechanically gated sodium channel, which could be fast. We could have mechanically gated calcium channels, which could be slow. And these add further to the varieties of the channels and gates. I generally do use a code like the gates of the channels are like the shopping for the girls. The girls shopping, when they go for shopping, they have a variety, they have a huge variety of clothes. Similarly, for the channels, there is a huge variety of channels and the gating behavior which is available for the cell membrane. So we have time gated channels, or example is pacemaker cell. So here all, let us just revise what have we done so far. We are onto simple diffusion. The substances are moving from higher to lower concentration. We have the types of channels, a leaky channels and a gated channels, and the gates of the channels open on different stimuluses. Further, suppose if a channel is for water molecules, because even water molecules cannot cross the cell membrane directly. Water cannot cross the cell membrane directly because of the lipid bilayer nature. So water, we have pores. For the water molecules, we have pores in a cell membrane. So if suppose we have to allow water to move, then what would happen? We have a pore which is present across the cell membrane, and these pores, they are generally always open. Pores are generally simple pore like structure. They are water filled channels, so they are always open, and the substance they move, or you can say water to be more specific, water moves either from outside to inside or from inside to outside through these pores. There is no direction specific movement of the water. Why? Because water always moves by osmosis, which we'll be covering in detail in the further session. So for water, we don't say that water is specifically from outside to inside, or specifically is moving from inside to outside. No, the movement of the water depends upon the salt concentration across the membrane. All right, so we have pores, and because they are water pores, they are also called as aquaporins. They are also called as aquaporins. So aquaporins are the water channels which allow the movement of water across the cell membrane. So we have channels, we have pores, and the last one, where the substances are moving through lipid bilayer, comes under the category of the simple diffusion. Let us go with the last one, and that is the substance they are moving through lipid bilayer. So lipid bilayer, which type of substance will move directly through lipid bilayer? They don't require channels, they don't require pores, but they will always move from higher concentration to lower concentration. A very simple example is oxygen. Oxygen always moves from ECF to ICF because cell needs oxygen. The mammalian cell, they need oxygen. The mammalian cell doesn't give oxygen, it takes oxygen. So oxygen always moving from ECF to ICF directly via lipid bilayer. So there is no hindrances. There is no you can say a bondage or a boundary which can actually decide that from this side the oxygen can move and from this side the oxygen cannot move. Oxygen can freely move from any part of the cell membrane because it directly crosses the lipid bilayer. Similarly, carbon dioxide also move through lipid bilayer, but it moves from inside to outside the cell membrane through lipid bilayer. Because cell is metabolically active, so cell when functions creates more of carbon dioxide and carbon dioxide is removed directly through lipid bilayer. So oxygen and carbon dioxide, they don't have to wait for the channels or the pores or for getting behavior. The moment cell needs oxygen, oxygen is available, the cell takes oxygen immediately. The moment there is CO2 inside the cell produced, the cell immediately gives out CO2. So these molecules and other gases like nitrogen or helium, the gases or the molecules which are very small, less than 400 daltons. Remember the word, less than 400 daltons. The size should be less than 400 daltons. And if they are lipid soluble, they can cross the lipid bilayer directly. So small molecules, lipid soluble, can cross the lipid bilayer directly. So here we have covered a very nice portion about simple diffusion, how it is occurring and how the substances are moving. All right. So this is one of the part of simple diffusion we have discussed. Now, the simple diffusion is not very constant. It might change. The rate of diffusion might change. The substance either move very rapidly or the substance either move very slowly. There are certain factors which determines this rate of diffusion. Certain factors which determine the rate of this diffusion. Say for example a temperature. When temperature increases, the momentum of the molecules and ions also increase. So the rate of diffusion also increases. Suppose if you are preparing tea and in a boiling water you add some tea leaves, because the water is boiling, the flavor and the fragrance and the color of the tea leaves, it disperses very soon, very rapidly, because the temperature is increased. But if you do the same thing in a cold water, the fragrance and the color dispersion doesn't happen very fast. So the diffusion is temperature dependent. Temperature might increase the rate of diffusion or it might decrease the rate of diffusion. So in a similar way, there are certain factors, in fact there are many factors which affect the rate of diffusion. Let us list down those factors which affects the rate of diffusion. All right. So the next topic is the factors which affects the rate of diffusion. So let us go with the factors affecting, or they decide, factors affecting rate of diffusion. Let us list those factors which affects the rate of diffusion. Now I would like you to be interactive here. I will say a factor and you will just give a pause and you give a thought that whether this factor is directly proportional or whether this factor is inversely proportional. Say a factor directly proportional means if that particular factor is increasing, the rate of diffusion also increases. If that factor is decreasing, the rate of diffusion also decreases. Let us start with an example of first factor, say temperature. Temperature of the medium or the cell or of the body. So increase in temperature will increase the rate of diffusion or will it decrease the rate of diffusion? Remember, temperature will always directly affect the rate of diffusion. Means increase in temperature will increase the rate of diffusion and decrease in temperature will decrease the rate of diffusion. So temperature directly affects the rate of diffusion. So you can say temperature is directly proportional to the rate of diffusion, or you can say rate of diffusion is directly proportional to the temperature. ROD stands as a short form for rate of diffusion. Let us go with the second example. The second factor. After temperature, if I ask you the solubility of the molecule or the ion, how far the ion or molecule is soluble. Does the solubility affect their rate of diffusion directly or indirectly? Means more the solubility, more the diffusion, or lesser the diffusion? What do you think should be the answer? Yes, solubility is also directly affecting the rate of diffusion. More the solubility of a substance, more will be the rate of diffusion. Lesser the solubility of the substance, lesser will be the rate of diffusion. Remember, certain drugs which are very easily soluble, they show their effect very rapidly. Similarly, ions and molecules which are more soluble in the medium in the body, they have a direct relationship with the diffusion. So more the solubility, more is the rate of diffusion, and solubility also you can say it's directly proportional to rate of diffusion. Directly proportional. Okay, example, carbon dioxide and oxygen. Among oxygen and carbon dioxide is 20 times more soluble in lipid bilayer than oxygen. CO2 is 20 times more soluble than oxygen. So when it comes to movement across the cell membrane through lipid bilayer, the movement of oxygen is happening, but movement of carbon dioxide will be 20 times more faster as compared to oxygen through lipid bilayer. So the CO2 is more soluble than oxygen when it comes to solubility, and CO2 moves much more rapidly through the cell membrane than the oxygen itself. So the rapid rate of diffusion also depends upon the solubility. So we have temperature directly proportional to the rate of diffusion. We have solubility, which is also directly proportional to the rate of diffusion. Let us go with the third factor. The surface area available. For the diffusion. What do you think? More the surface area available, more the diffusion, or lesser the diffusion? What do you think about the surface area? Surface area means how much surface is available for the diffusion. More the surface, more the diffusion, or lesser the diffusion? Very right. More the surface, more will be the diffusion. So surface area is also directly proportional to the rate of diffusion. Example, there are certain areas in a body tissues which have more of surface area than the available area. Say lungs. Lungs have alveoli. Alveoli increases the surface area for gas exchange. We have intestine. Intestine have villi, and villi have more folds in the, so these villi and arrangement of the intestine, they increase the surface area for a faster absorption. Kidneys, renal system, nephrons have a very huge surface area in the kidney. So example, I've written the example over here. We have lungs, and we have kidney, or we can say the GI tract. Lungs, kidney, and GIT are some of the examples where you can say the surface area is more, and that's why the rate of diffusion is also more. So these three factors as of now, temperature, solubility, and surface area, they do affect the rate of diffusion. Let us go with the fourth one. Now, let us take a factor, say the thickness of the membrane. Thickness or the distance available for the diffusion. Thickness of the membrane, or you can say the distance for the diffusion, or you can say the distance. Means the substance has to move through certain distance to diffuse from one point to another. So will the thickness affect the diffusion directly or it's inversely? Means say, let us draw the diagram here. Suppose we have a membrane this much thick through which the diffusion is occurring, and we have a membrane, another example, let's say we have a membrane which is almost double the thickness. So the diffusion distance has increased. So in both the cases, either in A or B, where do you think the diffusion will be faster or the rate of diffusion will be more? A or B? A is a condition where the membrane is quite thin or the distance is quite small for the diffusion. B is the area where diffusion, the distance diffusion is quite more or the membrane is quite thicker. Of course, the answer is A. In A type of condition, the diffusion will be much more faster. So thickness is the criteria here. More the thickness, lesser the diffusion. Lesser the thickness, more the diffusion. So thickness of the membrane is inversely proportional. Remember, it is inversely proportional to the rate of diffusion. Thickness is inversely proportional to the rate of diffusion. So remember, alpha and 1 upon alpha are just an indication for directly proportional or indirectly proportional. So thickness of the membrane is inversely proportional to the rate of diffusion. Let us take one example here. Say lungs. In the lungs we have alveoli, and alveoli, they have pulmonary capillaries which just bypasses them for exchange of gases. Now normally the distance between the alveoli and the capillary is negligible. They have very thin distance which is almost negligible, so the gas easily diffuses from the alveoli to the capillary. There is no distance, actually there is no gap which is present. They are so close to each other, the distance is almost negligible. But a condition called as pulmonary edema, a condition called as pulmonary edema, where this distance between alveoli and the capillary increases drastically. And if this distance increases, you know, there will be decrease in the rate of diffusion. So a pulmonary edema will be a condition where the diffusion of oxygen will be greatly reduced, because of increase in the thickness of the distance or thickness of the membrane from alveoli to blood capillary. So these are the things which you are supposed to correlate, right, from fundamental physiology to the systemic physiology, or you can say disease or applied physiology. So we have so far discussed 4 factors. Number 1 is temperature, which is directly proportional to the rate of diffusion. Number 2 is solubility, which is also directly proportional to the rate of diffusion. Number 3, we have discussed the surface area. More the surface area, more is the rate of diffusion. Then number 4, we have discussed the thickness. More the thickness, lesser the rate of diffusion. Lesser the thickness, more the rate of diffusion. Number 5, let us go with the 5th one, which is the 5th factor. 5th factor is quite interesting one. The concentration gradient. The concentration gradient means the gradient of the concentration of the ions or molecules across the membrane. There was a very interesting question in MCQ which I'll be asking in the near future to you regarding this concentration gradient. Concentration gradient of the molecule or the ion or the substances. What do you mean by concentration gradient? See, we have substance across the cell membrane. We have substances across the cell membrane. Say sodium ion. Now sodium ion is more in the ECF and potassium ion is more in the ICF. But just more or less is not a sufficient explanation here. Sodium ion is generally 140 millimoles concentration, 140 millimoles per liter. Sodium ion is in concentration of 140 millimoles in the ECF side, and it is 14 millimoles in the interior of the cell membrane. So the gradient of the sodium is almost 140 by 10, that is 10 times. That is almost 10 times. Okay. So this is the gradient for sodium ion. Gradient, concentration gradient is the difference of the ionic concentration across either side. You have to compare both the sides on the outside as well as on the inside. So what is the difference between outside and inside concentration of a particular ion or a particular molecule? Whereas potassium, if you look for the potassium, potassium is 140 millimoles inside. I'm giving quite a specific number, but generally it's in range like 135 to 140 for the sodium ion. For potassium, it is 135 to 140 or 145. So potassium is 140 millimoles inside and it is 3.5 to 4 millimoles outside. 4 millimoles outside. You can see now the gradient is quite different. So for potassium, it would be 140 by 4, almost 35 times. 35 times. So you can say the gradient for sodium is almost 10 times and the gradient for potassium is almost 35 times. Let us imagine with this slope. So if I create a slope for sodium ion, 140 and 14. This will be the slope for sodium ion. Sodium ion is moving in this way. And let us say the potassium ion, 140 and a 4. 140 and a 4. So 140 and 4 will have more gradient and they will move more rapidly. Okay. So for sodium, the gradient is quite less. For potassium, the gradient is quite very high. So this gradient, this difference across the cell membrane determines the rate of diffusion. Now what do you think? More the gradient, more will be the diffusion or lesser the diffusion? The flow will be much more faster and will be higher or the lesser? Yes, more the gradient, more is the rate of diffusion. So concentration gradient, I can say, is again directly proportional to the rate of diffusion. More the concentration gradient, more is the rate of diffusion. This is the point which is very, very important for our further studies. So you have to remember this without fail. Concentration gradient is directly proportional to the rate of diffusion. More the gradient, more is the rate of diffusion. The sixth one, the sixth factor. Let us go with the sixth factor. The presence of channels. The presence of channels. Now, more the channels, more will be the rate of diffusion or lesser the rate of diffusion? Obviously, more the channels available, more will be the rate of diffusion. So, the channels concentration, or you can say channel number. So, more the channels, more is the rate of diffusion. There are certain hormones and neurotransmitters which actually show their effect by increasing the channels in the cell membrane. They increase the number of channels or transporters in the cell membrane and thereby they increase the rate of diffusion. I'll give you an example here. Insulin, do you know insulin? Insulin actually increases the number of glucose transporters and thereby it causes rapid or faster rate of glucose absorption. In this way, the channel number or channel concentration determines the rate of diffusion. Seventh factor. Let us give the seventh factor. The size of the molecule, and sometimes we commonly hear size does matter. Although it's a very funny one, but yeah, we say that size does matter. So yes, size does matter. So size of the molecule or the ion, size of the molecule or the ion. So size of the substance is, what do you think? Larger the substance, more the diffusion or lesser the diffusion? Size of the substance, or you can say a molecule or an ion. So larger molecule or ion will diffuse rapidly or will diffuse slowly. What do you think? We always say that the thinner will move much more faster than the thicker one. It's very common thing you should be able to understand. Say glucose molecule, very big, C6H12O6, whereas the sodium ion, very small one. So if these two have to compete for a movement, definitely sodium ion movement will be much more faster. So size of the substance, smaller the size, more the rate of diffusion. I'll repeat, lesser the size, more is the rate of diffusion. More the size, lesser the rate of diffusion. So size of substance will be inversely proportional to the rate of diffusion. There is one very interesting concept here. One of the very interesting example I would like to quote here. You know, in terms of chemistry, in terms of chemistry, a potassium ion, a potassium ion is actually bigger than the sodium ion. A potassium ion is actually bigger than the sodium ion. A sodium ion is quite a smaller ion as compared to potassium. Okay, so I'll just make a circle here. So this is the sodium ion, and let the bigger circle for the potassium ion. So chemically, practically speaking, a potassium ion is quite a larger ion, whereas sodium ion is smaller ion. But when it comes to the cellular environment, you know, sodium ion actually shows lesser diffusion on the size basis. Why? Just take in this way that sodium ion is like a celebrity and potassium ion is a non-celebrity. So what happens when a celebrity moves in a crowd? You know, the celebrity is getting and and surrounded by the crowd across it. So sodium ion is a very strong hydrophilic. It has got a very strong attraction for the water molecules. So the water molecules, they gather around sodium ion, causing the sodium ion to become much more larger than the potassium ion. Potassium ion is non-celebrity, so it doesn't attract the neighboring water molecules, and hence potassium ion now looks quite smaller in terms of sodium ion. So sodium ion is always hydrated. You can say sodium ion is always hydrated, and therefore the sodium ion is practically bigger than the potassium ion, and therefore the sodium ion diffusion also becomes less than the potassium ion. Okay, so remember these are some of the very typical examples, or you can say features, which are quite exceptional cases which should be remembering here. Although, but one point stays: more the size, lesser the diffusion. So size of the substance is inversely proportional to the rate of diffusion, or you can say rate of diffusion is inversely proportional to the size of the substances. So more the size, lesser the diffusion; lesser the size, more the diffusion. So these are the factors which we have mentioned as of now. Let us just list them once again. We have temperature, we determine the rate of diffusion directly. We have solubility, we have surface area, we have concentration gradient, we have thickness of the membrane, and we have size of the molecule. Let us just browse them once again in a very rapid way. So I'll just uh, zoom out them. So we'll see we have temperature, solubility, surface area, thickness, concentration gradient, channels numbers or channel concentration, and the size of substance, which determine the rate of diffusion. Last but not least, one more factor. Factors, there is a huge list of factors, but at least we should cover some of the very important factors which determine the rate of diffusion and which are very important for our further studies. Let us go with one more. I'll add one more factor which also determines the rate of diffusion. Which one is that? And that is called as a voltage gradient. A voltage gradient is another example, or you can say another factor which determines the rate of diffusion. Voltage gradient, one of the very interesting one. So what is the relationship? Let us go with one of the explanation here. Say we have a cell membrane. All right. In and we have two cases, one a case A and a case B. Let us let them out, a case A and a case B. In case A, we have sodium ion on one side. Similarly, for the case B also we have sodium ion on one side. Now, in this particular situation, in this particular A situation, uh, on the other side of the membrane, there is no voltage. There is no voltage present. It's 0 millivolt. It is almost 0 millivolt. There is no voltage changes on the other side of the membrane. But sodium ion is in higher concentration. Sodium ion is in higher concentration. So sodium ion will diffuse. Sodium ion will diffuse, but we don't know how much it's going to diffuse. But let us go with the B one. Let us compare it with the B one. In the B case scenario, on the other side of the membrane, we actually create a voltage of say minus 100 millivolts. You know, voltage can be a positive and can be a negative. So we have created a negative voltage of minus 100 millivolts. Now what do you think will happen in the B case? The sodium diffusion will be more or less in the case B. On on the A side, there is no voltage gradient, but on the B side we have actually created a negative voltage of minus 100 millivolt. Now, this negative voltage would definitely attract more and more of positive ions. So sodium diffusion will be faster. A negative voltage will pull the sodium ions. So this will cause more and more sodium ion to move. So voltage gradient is the difference between a positive and negative voltage in either cases. So more the voltage gradient, more will be the rate of diffusion. More the voltage gradient, more will be the rate of diffusion. So remember this, one of the last but very interesting factor. Voltage gradient also determines the rate of diffusion. More the voltage gradient, more will be the rate of diffusion. So this is all about simple diffusion. We have covered what is simple diffusion, channels, pores, lipid bilayer, and also the factors which affects the rate of diffusion. Next, we'll be discussing about facilitated diffusion. So what is facilitated diffusion will be coming in the next session. Then, thank you.